If it were dn, the b would just be range over 0 and 1. That doesn't change because you've also got b squared z, right? But if it's n here, you'd have a to the n as e. So that means you could have a 1 to n minus 1, right? But here's a concrete case for d6. All right. Now a few other little results might need. Any element raised to power 0 is just a unit, right, by definition. And because b squared is the unit, b inverse equals b. I think we proved that a while back. But if any element squared is the unit, its inverse is itself. Right? So we'll use that a bit later. Okay. So G has this general form. Okay, b to the I, a to the j. All right. So plug in. So we're now going to put a cubed here, and work this out and see if the result belongs to h. In other words, is it e or is it a cubed? If it belongs to h, it must be either. It must be one of those two. It must be either e or it must be a cubed. Right. All right. So here's your general form for G. So plug it in here. So you've got G inverse a cubed G. G inverse a cubed G. Okay. So you got a product here. Take the inverse. So this will get rewritten as a to the minus j b to the minus I. Alright. Okay. Now if I is 0, now see you have two possibilities now. I can be 0 or 1. Okay? Here. I is 0 or 1. So let's do the two cases. Now if I is 0, these both become e, so that they disappear. So you're left with a minus j, a cubed, that's e, a cubed, aj, right? Now they're all a's now. So you can just add these powers, right? So the j's cancel and you're just left with a cubed. Oh, that belongs to h, right? So in the case when I is 0, your this, g inverse a cubed g, is just a cubed, so it belongs to your h. Right? Now, the other case, when I is 1, you will get now wait a minute, I changed that just before. Now strictly speaking, it should be b to the minus I. So b to the minus I, that's the same thing as b inverse to the I, okay? But b squared's e, so b inverse is itself, so it's just b to the I. Right? So, I don't have to put a minus I here. Okay, now, so I is 1, so b to the I a cubed, b to the I is just b a cubed b, right? Because I is now 1, I is 1. So we've got that, b a cubed b. Now you can rewrite that in this form. Now that's a trick, because now b squared's e, right? So I'm just saying effectively a, e, b, right? So I get it in this form. So these are all tricks, but it works. So what is BAB? So here's another trick. BAB is EBAB. You just put an E in front of it, and I can rewrite E as A inverse A, which is obviously E, right? But now I have three terms. I have three elements in the middle product of form ABA. Now here, ABA is B. That's one of the relations for a dihedral group, ABA equals B. That's, that's the motivation behind these tricks. So I can rewrite this ABA here as B, right? So that ABA just becomes B. So I get A inverse B, B. And BB is just B squared, and B squared is E, right? So I'm just left with A inverse. So BAB equals A inverse, right? But I got BAB 3 times here, cubed. So I'll get A inverse 3 times, which is A to the minus 3. Now for D6, what is A to the minus 3? Well, it's this number here. But if this were n, what's the inverse of A minus 3? It would be n minus 3. But in this case, n is 6. So A to the minus 3 is the same as A to the 6th minus 3, which is A cubed. Aha! A cubed is one of our members of H. So A cubed belongs to H. Alright? Therefore, for any member of G, we've got this. Right? We've covered all cases, and the results are either E or A cubed. Okay? So we've got that. Therefore, we have shown that H is normal, because we've shown this. And by showing this, from theorem 59, if you have this, you have G inverse HG equals H. Right? Remember that from previous session? Right, so therefore H is normal, and therefore we can find a factor group, right? D6 divided by H, D6 slash H here. And that will be a group of what size? Well, now we can use this theory, right? What size will this factor group be? It's the size of your group, size of your G, divided by the size of your H. Well, what is the size of D6, your big group, big G? Well, it's twice the number of sides, twice the number of sides in your hexagon. So that's 12. Right? So the size of your group G is 12, and the size, you divide that by the size of your subgroup H, which is just 2. It only has 2 elements, right? The size of this is 2. So your quotient group, your factor group, will have size 6. Okay? And that means, if you think about it, because it's a quotient group, and if its size is 6, we are talking about 6 cosets, right? Because the members of quotient group are cosets. They're the cosets of your H, your normal group H, normal subgroup, right? Okay, now before I start, then here's sort of like the result. Here is the group. There's the table. That's the group table. But before we get there, we still need a bit of theory. Very, very useful, and I'll use this bit of theory in the problem solving. A lot of techniques now. Now, I think in an earlier session, I think I remarked that this theorem 46, the second part of theorem 46, is very useful. Now I'm going to use it now, and I will use it again several times in problem solving session. After this one, or maybe 2 sessions after this one. Right? So a bit of a reminder, what does theorem 46 second part say? It says that if any element of your set G, any element little x, if it belongs to a coset A, in other words coset of your normal subgroup H, that's assumed. So if X belongs to one of these cosets, then theorem 46, second part, says that that coset is actually XH. Right? So if X belongs to that coset A, then A is XH. Right, now that has consequences. So watch. Here's your group. Right? There. Now it's G6. Sorry, D6. G is D6. So the number of elements in D6 will be twice the number of sides, equilateral sides. So the order of this group will be 12. A and B are the generators, right? Here's your general forms. This is from the theory of dihedral groups. You're quite familiar with this now. Now watch the following logic. Now it's not spelled out too clearly in the text, so I had to scratch my head a bit. But here's the essence of it. Now the size of the group is 12. Okay. The size of the quotient group is 6. It's half. So as we go, think about it. As we go forming the cosets of all these elements, for some reason, half of them get eliminated. Now remember, when you find cosets of a group, quite often you'll get cosets of the same. You get repeats, and so you throw out the repeats. So half of the cosets generated by this group, all your little g's, the coset of the form little g h, right? So you'll be able to form 12 of them. But your quotient group only has 6 cosets, so you have 6 repeats, right? So how do you go about knowing which coset is a repeat of which other one, and why? Why is it a repeat? So here's a bit of theory that you'll find very useful. Okay, here's the reasoning. Have a look at this. Now a to the fourth. That's one of your members here, right? That's one of your members of G. It's one of the members of D6. It's a to the fourth, right? Now, can you see that member is a member of this coset? Does that make sense to you? Because what is H? Well, it consists of just 2 elements, right? E and A cubed. So if I multiply a to the fourth into that and that, so a to the fourth H will become a to the fourth, a to the 7th. Okay, but here you've got an a to the fourth. Here, so a to the fourth here is a member of a to the fourth H. Now that's a coset, right? By definition, because we just took any element. No, we took an element, this one, and it's a left coset. So a to the fourth H. So a to the fourth belongs to this coset, right? Call that coset A. And I put it here in quotes. That is coset A, right? Now, by theorem 46 second part, if X belongs to a coset, that coset is, it's equal to XH, right? So this coset A, in quotes, is equal to, X, in this case it's a to the fourth.